In class activity 16D, 1. Suppose you have a pair of strong magnets that attract each other. What happens as you move the magnets closer together? How does the force of attraction change as the distance between the magnets changes? Well, eventually, magnets, if you get them closer and closer, they're going to pull themselves together. So let's say eventually the magnets will pull themselves together and we won't be able to pull them or hold them apart. The force of attraction increases as the distance decreases, and it gets really strong when the distance is small. Objectives for the activity. You will understand how the formula for a rational function determines the behavior of its graph. You will be able to determine the behavior of the graph of a function on both sides of a vertical asymptote using algebra. Sketch the graphs of rational functions near vertical asymptotes without using a calculator or app. Find a formula for a rational function to match a given graph. 2. Many quantities in physics, such as the gravitational force between planets or the intensity of light transmitted from a source to a viewer, behave like the attraction between magnets. The closer together two objects are, the greater the magnitude of the gravitational attraction. For example, if two objects are placed on a number line, one at point 5 and the other at point x, the gravitational attraction between the two objects is proportional to f of x, where f of x is equal to 1 over the quantity x minus 5 squared. Part A, without graphing f, can you tell where the vertical asymptotes will be? How can you tell, and what happens to the gravitational force when x is near a vertical asymptote? Well, there'll be a vertical asymptote just by an inspection. We can see there's a vertical asymptote at x is equal to 5. Because x equals 5 is a 0 of the denominator of the function f. But it's not a 0 of the numerator. The gravitational force becomes very large as x approaches 5. Okay. Let's go on to part B. Part B, without graphing, explain how you know that f is always positive. Answer, let's see. The numerator is always positive because it is constant, and the denominator is always positive because it's squared. Okay. All right, so we could say part B, let's write this down. Whoops, sorry about that. Numerator is always positive because it's a constant greater than 0. Well, actually, it's x is equal to 1. That's the numerator. 1's always positive. And we could say the denominator is always positive because it's squared. Oh, just the last thing we wrote was the denominator always positive because it's squared. Maybe a little bit more accurate would be the denominator is always non-negative because it's squared. But we could say that. We'll just leave it at this for now. So for part 3, in class activity 16B, we investigated functions to model the time it takes to charge an empty battery as a function of the current supplied by the charger. We noticed that these functions could take negative values, and these negative values could model the time it takes for a full battery to discharge. Given suitable choices of units, such a function has the following form: g of x equals 1 over x minus 5. Using a graphing calculator or app to sketch the graphs of the functions f and g, include all vertical asymptotes in your sketch. How does behavior of these two functions differ near the asymptotes? Okay, so let's go to our calculator On the y1 line and the y2 line, I've entered in these two functions. Let's do y1 first, and I'm just going to graph this. And we see the vertical asymptote at x equals 5, and then we see the curve. The entire curve is above the x-axis. And let's go back to our y equals screen. I'll turn the y1 off and y2 will be on. And let's graph this. Here we have an asymptote, a vertical asymptote at x equals 5. But part of the graph is above the x-axis, part is below the x-axis. So let's go back and do a quick sketch on our paper with these. So this is the graph. We'll do F first. And there's x is equal to 5. And we have a curve like that. And then G, we'll do that one next. X equals 5 is again the asymptote. And then the right side here of the curve is above the x-axis, the left side below the x-axis. Okay, part 4. Consider the function h with the following formula. H of x is equal to x minus 2 over x plus 1 times x minus 3, and that x minus 3 is squared. See if you can answer the following questions without using a calculator or app. So for part A, it says on the following number line, label each x value where h of x is a 0 with a 0, and label each value where h has a vertical asymptote with an a. In the intervals between the points that you labeled, indicate whether the function h is positive or negative. Okay, so let's just scroll up here. There we go. And let's see, at -1, maybe we should see the function there. So at -1, we have a vertical asymptote. So let's put an A right there. We'll stay in the denominator. At +3, we have another vertical asymptote. And going up to the numerator, we can see at 2, +2, we have a 0. So I'll put a 0 above 2. Now, what we'd like to do, we can do this. We could take a value less than -1. So we're on the left side of the -1 asymptote and plug in a value. We could plug in -2. When we do that, if I plug in h of -2 and evaluate that, we are going to get positive values all the way down. If we're between -1 on the x-axis and +2, so if we plug in, you could plug in 0, you could plug in 1 to the h function, and your output is going to be negative. And now between 2 and 3, we'll do the same thing, and we would get a positive output. And greater than 3, if we plug in, say, h of 4, we would get positive values all the way up. So that's one way to visualize that. Part B, on the following axes, sketch the asymptotes that you found in part A, along with the parts of the graph of h that are near the asymptotes. Don't worry about portions of the graph that are not near any asymptotes. Okay, so at -1, let me scroll up here. At -1, we have an asymptote. And at +3, we have a vertical asymptote. All right. And it said, let me read this again on the following axis. Sketch the asymptotes that we found in A, along with the parts of the graph of H that are near the asymptotes. Okay, so if we start with -1, the asymptote here, x equals -1, we're going to be on the left side of that, we're going to be positive. So we'll have a curve, that looks like that somewhere. And on the right side, we're going to be negative. So we'll be down here like that. And then for the 3, the x equals 3 asymptote, it looks like on both sides of this asymptote, we're going to be positive. So it will look like that. Let's go to part C. There it is. Part C says explain how you can use algebra to predict the shape of the graph of a rational function. Here it's vertical asymptotes. Well, one thing we could do is we could figure out whether the function is positive or negative in the intervals on each side of the asymptotes, which is basically what we did. If the function is positive, it approaches the upper part of the asymptote. If the function is negative, it approaches the lower parts. Let's go on to 5. Without using any graphing technology, sketch a graph showing the location of the vertical asymptotes of the following function, and sketch the parts of the graph of the function near these asymptotes. Don't worry about graphing the parts of the graph that aren't near any asymptotes. And then it says check your work using a graphing calculator or app. Okay, we can do that. So we're going to concentrate on function k here. And it may be easier to, let's factor the denominator. If we rewrite this, I'm just going to put an equal sign here and continue writing this with a factor denominator. So we have a trinomial x squared minus x minus 6. If we factor that into 2 binomials, we'll get what, x plus 2 and then x3, so minus 3. And then we still have the x plus 4, which we'll just copy down. So there we go. So what we can see here is there are going to be asymptotes at x equals negative 4 and 3. So at x equals negative 4 and x equals 3. And then for the other factor, there's going to be a removable discontinuity at x equals 2. Okay. Move. Cool. So x equals negative 2. There's a removable discontinuity. We could call that a hole. And we're supposed to graph this as well, or parts of this. That's just, there we go. Negative 4. And then positive 3. Okay, so if we go ahead and finish this, we want to draw the part of the curve that's near the asymptote. So if I pick a value less than negative 4 to input here, we are going to get a positive value out. So we're going to have a curve that's up above the x-axis. If I pick a value between negative 4 and greater than negative 4 but less than 3, we'll get a negative value. So we'll be below the axis there. And then let's see, if I pick another value for x that is close to 3 but less than 3, we'll get a negative value. And then greater than x equals 3, we are going to get a positive value. All right, let's just move this up here. Part 6, it says guess at a formula for the function shown, then use a graphing calculator or app to check to see how close our guess is. Okay, guessing at a formula. So we're looking at this graph for number 6, and we see that we have a vertical asymptote at x equals -1, x equals 1, and x equals 3. So let's write the denominator here. I'm just going to write f of x is equal to, and a fraction. So -1, so x plus 1, that quantity squared. And I'm looking at the vertical asymptote at -1, and notice that both sides, the curve is below the x-axis, so it's the same. So I'm going to square that, and then I have x minus 1. That is, the curve is on below and above the x-axis, and then x minus 3. Again, part of the curve on the left is below the axis, above on the right side of the asymptote at x equals 3. And we can also see that we have a 0 at 2. So x minus 2 could be the numerator. Okay, so if we go to our calculator one more time, we enter this in. I have it on the y1 screen or line and graph this, and that looks pretty close to what we had. Go back here, and that is the end of this video.